welcome to another module in this massive open online course. So, we are looking at different forms of pulse modulation. We have looked at pulse amplitude modulation, we have looked at delta modulation, alright, which is based on encoding the differences, which is the differential modulation scheme. So, in this module, let us start looking at another pulse modulation scheme, that is differential pulse coded modulation or DPCM. Okay. So, we start a new module in which we want to start looking at differential pulse coded modulation. This is differential pulse coded modulation, correct, as the name implies, and this is abbreviated as DPCM for differential pulse coded modulation. And this is based on the principle that, for instance, when you have natural signals such as video signals and audio signals, they have a very high level of correlation. So, rather than encoding the samples similar to delta modulation, one can encode the differences between the samples, but it is more sophisticated than delta modulation, alright. So, the key principle behind that is that naturally occurring signals such as video and audio signals have a very high these are very highly correlated, correct. Hence, one can, so the bit rate, so these have very high redundancy, high correlation, which implies also that these have a very high redundancy, correct. So, high correlation also implies that so these have a very high redundancy, which implies that the bit rate can be, therefore, the bit rate can be significantly reduced by reducing the redundancy, right. So, the bit rate can be significantly reduced, by reducing the redundancy of the. So, they have a lot of, they are correlated, which leads to a lot of redundancy, alright. So, the bit rate, right, which means the bit rate, there is a number of bits required to encode each sample, can be significantly reduced by reducing the redundancy of this signal, alright, and this is what DPCM tries to achieve, okay. And DPCM, the way DPCM achieves this is reducing the redundancy. DPCM employs, so achieves this or reduces the redundancy, achieve this by predicting the signal Mn by predicting the signal sample Mn and followed by encoding the difference. So, what we have is, and we encode the difference, that is the differential modulation aspect. So, what we have is, if you really look at it, we have a signal with a lot of redundancy, all right, a lot of redundancy, all right, and this leads to predictability of the signal. Because of this redundancy, one can predict the signal, all right, and therefore, rather than quantizing the entire signal, one can predict the signal, look at the difference between the signal sample and the prediction, and then encode the difference. That results in a significant efficiency, a significant improvement in the quality of the quantization and quality of the compression. Okay. So, what we are doing is basically we are deriving a prediction of the signal. So, MPN, this is a predicted sample of the signal at time instance. This is a prediction of the signal at time instant n. This is obtained as f of MQ n minus 1, MQ n minus 2, so on up to MQ n minus L. So, what we are doing is basically we are using L past samples. So, if you look at this MQ n minus 1, MQ n minus 2, MQ n minus L, these are the L past quantized or basically reconstructed samples. Okay, these are the L past samples. So, we are using the L past reconstructed samples to predict the signal at time instant n. Then we subtract this prediction from M and encode the difference. All right. Now, in delta modulation, this prediction function is very simple. MP of n is simply MQ of n minus 1. That is the last quantized samples. Okay. So, for delta modulation, now if you remember delta modulation, for delta modulation, we use a simple prediction function, that is MP of n is simply MQ of n minus 1. This is the prediction function for, this is your prediction function for the delta modulation. MP of n equals MQ of n minus 1. Okay, this is a prediction for delta modulation. DPCM generalizes it. The prediction prediction need not necessarily be simply MQ of n minus 1, but one can use not just one sample, but past L quantized samples to improve the quality of prediction. Therefore, the better the quality of the prediction, right, the better the quality of prediction, the better is the quantization, higher is the efficiency of quantization. So, we have the prediction, all right. So, we are using the L past samples, quantized or reconstructed samples, your MQ of n minus 1, MQ of n minus 2, MQ of n minus 1, these are L past quantized samples, not just past samples, these are L past quantized samples. These are the L past quantized samples, all right. F, the function f is your prediction function, correct. We are using the L past quantized samples in the function f. F equals there are ways to construct the optimal prediction function. Okay. This prediction function can be suitably designed. The prediction function has to be appropriately designed. Can be the prediction function f is not fixed, but it can be suitably designed. Various that depends on the appropriate signal. It takes the signal characteristics, more importantly the statistical properties of the signal into consideration to appropriately design the best prediction function. Alright. Now, better prediction implies a higher efficiency. The better the prediction, the higher the efficiency. Better prediction implies a higher efficiency. Okay. That is the bottom line in DPCM. Now, how do we use this prediction in DPCM? In DPCM, what we do in differential pulse coded modulation, we have the signal Mn, signal sample Mn. From this signal sample, we subtract its prediction MP of n, that gives rise to E of n. So, E of n, so at every time instant n we have a prediction MP on m of the signal. Now, from Mn we subtract this prediction MP of n, we get En. So, En is the prediction error. Okay. So, this En is the prediction error. Okay. You can think of this as a now this prediction error is quantized. So, now what we have is we quantize this prediction error to get the quantized error is Q of E of n. This is your quantized prediction error. You get the quantized prediction error. Okay. Now, better the prediction, lower the prediction error, the better the quantization. If the prediction error is lower, which means if its dynamic error range is lower, then the quantization can be made more efficient, right. For if the for the same number of bits, if the dynamic range is lower, then the quantization error is lower, correct. So, if the prediction is good, right, if the prediction is good means MP of n is very accurate representation of M of n. E of n, which is equal to the prediction error is lower. This implies, right, this implies the quantization, this implies that the quantization is very efficient. Therefore, we need very accurate prediction. Alright, in DPCM we need very accurate prediction. Okay. Now, EQ of n is the quantized prediction error. Now, MQ of n, the reconstructed error, reconstructed signal is similar to delta modulation, that is simply your, well, that is simply your MP of n, the prediction. Remember in DPCM this is simply MQ of n minus 1, this is MP of n plus EQ of n. Okay. This is your reconstruction. Okay. This is your reconstruction. Okay. So, this is the reconstruction. This is in fact the identical thing that is going to be used at the this is your reconstruction. Okay. And now in addition, one other thing that you have to observe, this q of n need not be need not be 1 bit. For instance, delta modulation, it is simply delta times sine of a, that is plus or minus delta. However, in DPCM it can be an arbitrary number of bits. Of course, the larger the number of bits, the better the quantization, alright, the better the reconstruction or better the quality. Okay. So, this q can be of an arbitrary number of bits, okay, can have arbitrary number of bits. This q can have an arbitrary number of bits. Okay. And finally, the prediction. The prediction MP of n, or rather you will have your MP of n, or we can write this over here, maybe we can write this over here, you have your Dpcm and your MP of n, the prediction, equals f, where f is the prediction function, mq of n minus 1 up to mq of n minus l. Okay. So, this is the first step, this is the second step, okay, where you are forming the prediction error, this is the third step, mq of n minus 1 equals mq, okay, this is the third step, eq of, that is quantization error, this is the third step, and this is the fourth step, that is reconstruction, mq of n equals mp of n plus mq or mp of n plus eq of n. Now, we can draw a schematic diagram for this game. For DPCM, okay, this is a schematic diagram for differential pulse coded modulation. Now, we have your signal sample m of n, similar to delta modulation, we take in the sample at every time instant n. Okay. Now, from this we subtract the prediction, this is minus mp of n, that is the prediction. Okay, we subtract the prediction mp of n, okay, that gives us E of n, which is quantized. This is your quantizer to get the quantized error EQ of n. And now, this quantized error, as we know, this is passed through the encoder to convert it into a bit stream. This is passed through the encoder, and this is either transmitted or stored. The encoded bit stream is either transmitted or stored. Transmitted being transmitted over a channel, if this is a communication system, transmitted over a channel, or this is simply stored. Now, this EQ of n, as we already seen, this is combined with the prediction MP of n. So, MP of n and EQ of n, that gives rise to MQ of n, that is a quantized sample. Now, this passes through a prediction filter. or basically your f, which is basically the prediction function, correct. So, we pass this through the prediction function, and the prediction function takes the past values, L past values of, so this is your prediction, this is your prediction function. Okay. So, this is basically the schematic. Okay. So, you have to pass it through the prediction function. Okay. Now, in the case of delta modulation, this prediction function is simply Z inverse. If you remember, that is simply delay, that is MQN is delayed, MQN minus 1 itself is the prediction function. So, for delta modulation, this is simple delay. For DPCM, it can be constructed very efficiently, taking also the statistical properties of the signal into consideration. Okay. So, let us note that also for delta modulation, this is simply Z inverse, where Z inverse is the delay, okay, the delay block, single sample delay. Okay. Now, let us now look at the reconstruction. Let us now look at the reconstruction. Now, for reconstruction we have already seen, it is very simple. Reconstruction is, you have your, for reconstruction, DPCM reconstruction, for DPCM reconstruction you have, well, you have to first generate the prediction MP of n is f of MQ n minus 1 up to MQ n minus L, and then you have your MQN reconstructed value at time instant n is your MP of n, MP of n plus EQ of n. Okay. So, this is the quantized error at time instant. Okay. So, let me describe these quantities. MQ of n is reconstructed sample this is a reconstructed sample at time instant n, this is the predicted sample at time instant n from the past L quantized sample, predicted sample at time instant n, and EQ of n, EQ of n is the well quantized error at time instant n. At quantized error at time instant n. Okay. So, that is a very simple reconstruction. We simply have to predict the sample MP of n at time instant of n, MP of n the predicted sample plus the quantized error EQ of n gives MQ plus the quantized error EQ of n gives MQ of n, that is a quantized sample or the reconstructed sample at time instant n. Alright. So, let us draw a schematic for the reconstruction. The schematic for the reconstruction will be very simple. You have your input, okay, from the channel or your storage device, which is the encoded input. You pass it through a decoder. Remember, this is an encoded bit stream. You pass it through the decoder, all right. EQN is encoded to produce the bit stream. The encoded bit stream is passed through the decoder, that gives us again EQ of n, that is the quantized error. To EQ of n you add MP of n. So, to EQ of n you add MP of n, okay, that gives rise to our output MQ of, that gives rise to the output MQ of n. Now, this output you also pass through the prediction filter, again the same prediction function, okay, you pass. So, this gives you your this gives you your, this is your prediction function, you take in MQ of n, L pass samples of MQ of n, and so this is your output. So, naturally this involves feedback, as you can see. So, this is your prediction function, this is your prediction function. So, this is your prediction function, you take the reconstructed output, take the past L samples, pass it through the prediction function, generate the prediction. From the decoder you get the quantized error, to the prediction add the decoded error, decoded quantized error, that is MP of n plus EQ of n, that gives rise to MQ of n, which is the reconstructed sample at time instant. Alright. So, that is basically in summary differential predictive DPCM, differential pulse coded modulation. Alright, it uses, it is a differential encoded scheme. It's, you can think of it as a generalization of delta modulation. In delta modulation we only use the reconstructed past sample as the prediction, and of course, it is a single bit quantization. DPCM generalizes that, it generalizes by building a better function for the prediction, which uses not just a single pass samples, but L pass samples, and also the error, that is m minus MP of n, that is a prediction error En, can be quantized using an arbitrary number of bits. And DPCM is a very efficient predictions, is a very efficient encoding scheme, as I have already told you. It is a pulse modulation scheme, it can also be used for compression, both for transmission and compression. It is a very efficient compression scheme, and it is used in almost all of the modern audio video encoding standards. For instance, you can think of your JPEG, MPEG and so on. Alright. So, DPCM is a very efficient prediction technique, or a very efficient pulse coded modulation technique, coded modulation technique, which is used for efficiently quantizing and compressing or transmitting the signal over a communication system. Alright. So, it has a lot of relevance in modern storage as compression as well as communication application. Alright. So, we will stop this and we will continue with other aspects in the subsequent modules.